All right. So, anybody have a specific problem in here they want to start with? Let's just look at 352. You bet. Okay, determine the tension developed in cables AB and AC and the force developed along strut AD for equilibrium of the 400-pound crate. So what type of problem is this?
3D equilibrium?
Sort of 3D equilibrium. It is 3D equilibrium, but is it 3D equilibrium of a rigid body or of a point? Of a point, right? What's the difference? So, whether you can solve for moments or not, right? All of the forces are concurrent in this setup, right? So at A, all the forces go through A. So if we solve for some of the forces in X, Y, and Z at A, we'll get the answer. If it were a rigid body, then we would all the forces wouldn't be concurrent, and we'd need to figure out use the sum of the moments equations. Okay. So this indeed is some of the forces X, Y, Z, 3D equilibrium of a particle or a point. How do we need to start this problem? Free body diagram would be a good place to start, right? So our free body diagram, it's pretty easy in these ones to draw the body, since it's a particle. Okay. What forces are acting on my particle? Okay, so I'm going to have some TAB. I'm going to have some TAC. And which way do you want to draw TAD? Do you want to draw it in compression or in tension? Yeah, so our rule is if we don't know, we draw them all in tension, right? But this one we know it has to be in compression because it's the only thing capable of compression, and if we don't do it, we're going to be accelerating to the left. So let's go ahead and live on the wild side, right? It'll still work with TAD being compression, and then the load of 400 pounds. Okay. Well, now we need to be able to figure out the components of TAB, TAC, and TAD that are in the X, Y, and Z directions. What's our trick for doing that? Unit vectors, right? So to find a unit vector that TAB acts along, I need to first find the position vector, RAB, and then find the unit vector, right? So let's do that. RAB. In the X direction, it looks like we go from 0 to -2. In the Y direction, we go from 6 to 0. And in the Z direction, we go from 2.5 to 4. And while we're doing these, let's do our AC. In the X direction, I go from 0 to 2. In the Y direction, I go from 6 to 0. And in the Z direction, I go from 2.5 to 3.5. Excuse me, from 2.5 to 5.5, which would give me 3. And finally, let's do our DA. Right, I should change this to really be DA since I drew it going from D to A. RDA, in the X direction, I start at 0, end at 0, so I have 0 change in the I hat. In the Y direction, I go from 0 to 6, so I have +6 in the J hat. And in the Z direction, I go from 0 to 2.5, so +2.5 K hat. Okay. So at this point, I would get out my calculator. right? And I would go to catalog, and then I would type in the letter U, and go down here to unit vector. Then I would hit my square bracket and do my first one, -2, comma, -6, comma, 1.5. Close the square bracket and enter. And this is going to give me the unit vector of AB is -0.307 or 308. I hat minus 0.923 J hat plus 0.231 K hat. Let's do the same thing again, except now we'll have 2, -6, and 3. And the unit vector for AC is going to be 0.285 I hat minus 0.857 J hat plus 0.429 K hat. And then let's do UDA. We'll get 0 I hat plus 0.923 J hat plus 0.385 K hat. Okay. Now we need to write our force summation equation. So sum the forces in the x, they've got to be equal to 0. X is positive that way. So I'll have TAB, its component in the x direction is -0.308 plus 0.285 TAC plus 0 TAD equals 0. Sum of the forces in the y equals 0. That's this away. So for TAB, it looks like I have -0.923 TAB, -0.857 TAC, plus 0.923 TAD equals 0. And lastly, sum of the forces in Z equals 0. That's going to be positive. So in the Z direction, I'll have 0.231 TAB plus 0.429 TAC plus 0.385 TAD equals 400. Right? Because I got that 400-pound mama jama in there. So now to solve this, I don't do it by substitution, right? I'm going to come up and use my solver. So F2, solve. First equation, -0.308x plus 0.285y equals 0. Catalog and -0.923x minus 0.857y plus 0.923z equals 0. And 0.231x plus 0.429y plus 0.385z z equals 400, comma, curly bracket, x, comma, y, comma, z, close the curly bracket, close the parentheses, and solve. Okay? And it looks like from this, we get that TAC is going to be equal to 273 pounds. I'm sorry, that's TAB. TAC is going to be equal to 295 pounds. And TDA is going to be equal to 547 pounds. It's not what you got. Anybody else type it in with me? You got this? Okay. So one of the things that I like to do when I solve these is make sure that I keep all of my variables in line so that I don't accidentally make a mistake. So like I put TAB first in all of them, TAC second in all of them, and TAD third. And I don't neglect to put TAD in this one so that I know I have X, Y, Z, and these are X, Y, and Z in my calculator variables. Okay. Okay. All right. Yeah. Okay. Questions on this guy? All right. How about let's take a look at this one. Okay, good question. So other than friction and wedges and screws, does this packet cover what's going to be on the exam? Gosh, I think it pretty much does. It's hard for me to think what else is missing if you do the whole packet. So what type of problem is 5.8 here?
Rigid body.
Rigid body what?
3D.
3D equilibrium of a rigid body, right? So now we do have size. So this will be a good practice for us. I think this is one where you guys probably want to brush up on. Determine the X and Z components of reaction at the journal bearing at A. Right, so we know that right here we have some A sub Z and some A sub X. And the tension in chords BC and BD necessary for equilibrium of the rod. Okay, so then there's some TBC and TBD. Right? And then we know we have an 800-pound load there and a 350-pound load there. All right. Looks like we have 1, 2, 3, 4 unknowns. Right? We should be able to solve this because how many equations can we get? 6, right? How should we start? Find the vectors of BC and BD. Is that what you're thinking? Okay. So let's do that. Let's find the vectors for BC and BD. How do we do that? We always start with what? Yep, the position vector. So RBD. So I'm starting right here, and to get to D, it looks like in the X direction, kind of hard to tell, but it looks like you don't move in the X. In the Y direction, it looks like I move 3 meters. And in the Z direction, I move 4 meters. Which means that's a 3, 4, 5, so we can just do our unit vector right off the bat in our heads and say that the unit vector is 0I plus 0.6J plus 0.8K. And our BC looks like it's the same, except -3 in the J direction, +4 in the K hat. So unit vector BC would be 0I minus 0.6J plus 0.8K, right? So now what? Yeah, so we have to have the reactions at the journal bearing. So we have AX and AZ. Those are going to be our reactions there. Yeah, start writing our equations. So we can start writing our equations and start with sum of the forces in the X has to be equal to 0. So X is like that. What has a component in the X direction? Well, it looks like AX certainly does. I don't see anything else with a component in the X direction, do you? There's one. Right? Let's try some of the forces in the Y direction. What has forces in the Y? Well, it looks like TBC does, and it would be negative 0.6J, so negative 0.6 TBC. TBD does, plus 0.6 TBD. Anything else? F2 plus 350 newtons equals 0. Okay. Let's try some of the forces in the Z. Definitely have some AZ. We'll have some positive 0.6 TBC, sorry, 0.8. Plus 0.8 TBD. Minus 800 equals 0. So I have 1, 2, 3 unknowns and just 2 equations. So let's see, what's the easiest next equation? I only need one more. What's that? Moment about what? Moment about B. Ooh, yeah. I like that. Moment about B. Well, so we have to do it about an axis. So let's sum the moments about the x-axis at B. What's that?
But F2, you have to leave F2 out because it's on the axis.
But I have to leave F2 out because it's perpendicular. Yeah, you would, right? So the question is, would I leave F2 out because it's on the axes? And what Brandon is pointing out is that the axes, the x-axis through B goes right through there. So F2 goes through the axes, so it has no moment. So I'm a little concerned here, but let's give it a whirl. So the things that cause a moment about the x-axis that's going through B are none of these forces, not that force. So it would just be AZ, right? And it would be negative AZ times 3 meters, 6 meters. Yeah. I think it'd be 6 meters because it says it's 6 from B to the x-axis. Not very happy about this though. I don't think that's right either. Why don't you feel like that's right? The reason I don't like it is because we have 350 acting along the y-axis. They can counteract it in the y direction, but they can't counteract the moment that it would cause, right? Because if I sum the moments about the z-axis going through B, right. I don't think AX can be equal to 0. So what am I, how? Yeah, AZ I'm fine with it being 0. But I believe AX actually needs to be, oh gosh, 2, 6, so 3 times that, 1,050.
I don't know how you got that number, but please share.
So here's what I'm doing. I'm summing the moments about the z-axis at B. So z-axis is vertical. That would give me this being positive. So I'd have AX times 6 minus 350 times 2 has to equal 0. And I think what you'll find then is that AX would be 1,050 newtons. Yeah, so what do we do with the first equation? Is point B on the same, I think, looking at the picture, I think it's on the same YZ plane as B, yes? Is that what you're asking?
Has like more things they add in. add in like moments.
Yeah. Yeah, so I was kind of wondering if perhaps exactly what Joseph is saying is if perhaps they also have remember how I don't like how they use bearings in the book? Because they say that sometimes they can counteract a moment, right, about the z-axis, and that this could counteract a moment about the x-axis. So my guess is that that's what the difference is, right? Because if we put these in, then this can still be true where ax is equal to 0, right? Because now when I sum the moments about the z-axis, I would have plus mz of the journal bearing, right? And that has to equal 0. And what we would find out is, well, ax is still 0, so mz needs to equal 700 Newton meters. What's that? Yeah. So, yes, this is why I think we are here. Let's see. I don't know if this is from this book. Let's see if it is, because the answer would be available to us. Then we can see if they came up with a moment at the z. Ah, yes, it is. So R5.8. I think they have the answers to the review problems in here, don't they? Hope. Yep. Yep. It is precisely as I suspected. So if we look at 5.8, they are indeed adding in a moment at A about the z-axis when they do the moments about z, and a moment at x about the x-axis. And what they find is exactly what we just found, that the moment at A has to be 700 Newton meters. So this is what I don't like about how the book handles journal bearings, right? Because what they're saying is their free body diagram includes a moment reaction that a bearing can provide about x and z. And I don't think this makes any sense. This isn't how you design, that's not how you use a journal bearing. Okay, journal bearings are not meant to resist moments. So maybe a civil engineer would look at them that way, but not a mechanical engineer. Okay, so I won't give you something on the exam where it's unclear. Okay, I will tell you that it only resists in x and y, or it does have a moment where it is capable of resisting a moment. Okay, does everyone understand this process okay, though? You're not what?
We're not looking at moments.
Yep, so whenever you see a journal bearing, just assume that it has the reactions in x and y, and it doesn't have any moment reactions at it, unless I tell you otherwise. Okay, maybe I'll say a super fancy bearing that resists a moment. Okay. All right. How people feel about trusses? Pretty good? Skip, do you want a review problem on a truss or not? Do one? Okay.
I mean, unless people want to do something like
We can come back to it.
Come back to it? Okay. What number? 4118. Okay. Replace the loading acting on the beam by a single resultant force. Specify where the force acts measured from B. Okay. So we have three forces in a moment, and we want to find we want to replace them so that the beam feels the same load and specify where that force will be in relation to B. Okay? So essentially, we need to find the resultant of these forces and determine the moment that they cause about B. Right? So we'll start by saying, let's sum the forces in the X. Actually, just sum the forces in the X. We're not even setting them equal to 0. We're just summing the forces in the X. So in the X, it looks like I would have 450 cosine 60 minus 700 sine 30. Right? I think that's going to be 225 minus 350. So I think that's negative 125. Is that right?
Why don't we make it equal to 0?
Because, so the question is, why don't we make it equal to 0? Because what this is asking for is replace the loading acting on the beam by a single resultant force. So we're just trying to find the resultant force. So we're adding all of these up first, okay? So I think what we find is that in the resultant in the X direction has a magnitude of negative 125. So now let's sum the forces in the Y direction. Looks like I'll have negative 450 sine 60 minus 300 minus 700 cos 30 equals 0. That doesn't equal 0. I'm sorry. I'm just so used to saying equal to 0. I'm a terrible person. RY, anyone? I'm here negative 516.5. No? I put 300. Maybe. Anybody else get 516? Yeah. Negative what? That sounds better to me. Okay. Huh? All right. So then let's sum the moments about B. Yes. So the question was, is this how we're going to find where the position of this resultant is? So what we've done up to this point is we know that there is there's going to be some force, right, that acts down with a magnitude of 1295 and to the left with a magnitude of 125. And now we just need to figure out where is that from B. Okay? So we need to figure out the moment caused by these forces. So let's sum our moments about B. And we will have some of the moments about B. We're going to say counterclockwise is positive. So we'll have 450 sine 60. That's the force, times the lever arm of 4. That's going to be in the positive direction, minus 700 cos 30. That's the vertical force component right here, times its distance, 3, minus 1,500 Newton meters. Yes, so the question is, how come I didn't find the reactions at A and B? And the answer is because I don't care, right? Because right now it says replace the loading acting on the beam by a single resultant force. So it's saying simplify all of this into just one force at one location. And it doesn't tell us to include the reactions. Okay? So what did we find for the moment about B? We didn't forget the 1295 because remember that the 1295 and the 125 is just what the forces will be if I sum up all of these, right? So the 1295 and the 125 is what we will place here, but we need to, in order to know where to place it, we need to figure out what the moment is. Okay, so what's the moment? Negative 1759 Newton meters. Okay? So that means overall at B, we have a curly counterclockwise of 1759 Newton meters. So how do I figure out what X is? Yeah, so 1759 is equal to 1295 times X, right? Because I'm saying I need 1759's worth of twisty out of this 1295 force. So in order to do that, I'm moving it to the right some distance X. What is that distance, like 1.4? Is it actually 1.4?
Whoa, you're nice for that.
Wow. Okay. So now we know that
How did you do that?
I guessed.
Yes.
Yeah. Okay, so I'll explain how I did that. 1759, 1295. It's not quite 1.5 times, right? Because half of this would be about 650, which would be about, get us to about almost 1900. So I just said it's a little bit less than 1.5, must be 1.4.
Educated guess.
It was an educated guess, yes.
That's
Okay. It's going to be really sad if all you take from this class, though, Brandon, is that I can sometimes get lucky.
It would be really sad.
Okay. So any questions on this process? It's hard for us to go back and do this now, right? It's hard for us not to set things equal to 0 because we're so used to doing that. But what we were doing, all we were doing here is really a fancy find the resultant force, add the vectors, and give me the answer. Yeah, good question. So would I want you to turn it into one force that, looks like this? If you can't do that by this point, I don't really know what to tell you. And so I'm not going to actually be checking whether you can do that. I would take it either way. Like if you can get 1295 and 125 as two components, that's how I would leave it as an engineer, right? Because it would almost never be useful to me to know it not in X and Y. Yeah, it's a little bit of extra work using the Pythagorean theorem, which you learned hopefully a decade ago, So, all right. Next. Should we do the last machine design one, maybe? Okay. Operation of exhaust and intake valves in automobile engines consists of cam C, that's this guy down here, push rod DE, that's this guy, rocker arm EFG, which is pinned at F, and a spring and valve V. If the compression in the spring is 20 millimeters when the valve is open as shown, determine the normal force acting on the cam lobe at C. Assume the cam and bearings at H, I, and J are smooth. The spring has a stiffness of 300 Newton meters. Gosh, I don't know that this is even a machine design problem, unless I'm missing something ginormous. Okay? So we're told that the spring has a stiffness of 300 Newton meters. and we're told that it's compressed 20 millimeters. So we can figure out the force of the spring is going to be equal to 300 Newton meters times 0.020 meters. Is that 6 newtons? Okay. So then if we go up to EFG, I believe what's happening here is the spring is being compressed, so that means that the force of the spring is pushing up with 6 newtons. We'll have some F sub y, I guess, and F sub x. And then we'll have some E, right? This is a super easy problem, it seems like. 40 millimeters, 20. I need to figure out what FE is. What's the most direct way to do this? Yeah. Moment. Let's sum the moment about where, Brandon? F. Looks to me like F sub E is 12. Sorry, dang it. I thought it was 20. It's 25, so it's not 12. That I can't tell you then. It's going to be like 10? Yeah, it's going to be 10, isn't it? Is that right? Huh? 9.6. Dang it. Close but no cigar. I was not within 1%, no. Okay. That one was... no, I don't think so, because it has to be, so the question is, wouldn't it be negative? And the answer is no, because this is negative, so this one needs to be positive in order for us to equal 0, right? Or you could say, take this one to the other side, and you'll have to switch its sign. Okay. That was kind of a letdown as far as a machine problem goes. Like, let's try something a little bit more exciting than that. What is a cam lobe? Good question. A cam lobe, whenever you have a shaft, right, that spins, and then you put a bump on it. So this is the axis of rotation. This is called the lobe of the cam. And they're always used in applications like this where they move something that it's used to turn a rotational motion into a linear motion. Right? So I could have a block that sits on top of this, right? And as this spins, most of the time it would just sit against the shaft. But when that lobe comes around, it's going to make the block go up, right? So the lobe kind of causes linear motion from a rotary motion. Okay. Good question.
We found FE. So how is that? I thought the cam lobe was at C.
Yeah, I guess, but I would look at that and say, hey, it's a two-force member,
Oh, yeah.
right? So it's going to be the same. Okay. Let's try a frame. Yeah, this one looks good. Okay, so this one's not in your notes. Let's look at this here frame. See if you can find a blank spot. I'm gonna freeze this for just a second so you can get it in your notes. Okay. 6-76. Yep. Okay, so we're asked to find AY, AX, BY, BX. Can't solve this just easy peasy lemon squeezy, huh? Because these are both pin joints. You know, if this were just a roller or something, we could solve this, but it's not. So where are my two force members? Okay, E to F. This is a two force member. DC and CF. Sorry, CB is one continuous. Right, C to B is one continuous member. Okay. So like the two sides are continuous, and then there's just two struts that go across. All right, so it looks like EF is a two force and DC is a two force. Okay. So how do we proceed? Split it up. Draw individual free body diagrams. So let's start with DEA. Why can I write this TDC as only horizontal? Why doesn't, it's a pin joint, why doesn't it have a vertical component? Because this is a two-force member, right? So we know that the force has to be along its axis. Can I solve for these forces with this? Why can't I just solve right now, Liana? I have 1, 2, 3, 4 unknowns and 3 equations, okay? So would it make sense for me to draw a free body diagram of EF? Why not? This is a two-force member, right? We're not going to learn much there. Same thing with DC. So the other free body diagram I need to draw is CFB. On this, I'll have BY, BX. How about at F? What am I going to have? An arrow going up and to the left? Is my arrow going this way from F to E? Down and to the right. Why? It's actually in compression, but why the direction? Equal and opposite. Okay, so that means at C, TDC is going to be over this way. Oops, DC. So we've introduced 2 new variables, BY, BX, but by drawing a second free body diagram, we get 3 new equations. So now we have 6 equations and 6 unknowns. Okay, so let's write our 3 equations for DEA. Sum of the forces in the X has to be equal to 0. So 400 times, looks like 4.5, is that 1,000? No, it's 1,800, right? So we know we have a resultant of 1,800 newtons here. Minus TDC minus some part of TEF, right? And we have to figure out what part. So this is 2, 1.5, so that's a 3, 4, 5 triangle, right? This is 2, 1.5, or you could say this is 3, this is 4, and this is 5. So we're looking for the horizontal component of TEF, so that's going to be times 0.8, 4/5. What else do we have then? AX. Right? My 3, 4, 5 triangle here, it's telling me that this is on a 3, 4, 5 triangle. So the horizontal component would be 4/5 or 0.8. Sum of the forces in the Y. Well, it looks like I'll have 3/5 of TEF, so 0.6 TEF plus AY equals 0. Then I'm going to have to sum the moments about a point. Let's choose E. Choosing E because it gets rid of TEF and AY. So then I'm just left with TDC times 1.5 plus AX times 3 equals 0. So there's 3 equations with 4 unknowns, right? So these go with that guy. Now let's do the equations for this guy. Sum of the forces in the X equals 0. Looks like I'll have T DC plus 0.8 TEF plus BX equals 0. Sum them in the Y. BY minus 0.6 TEF equals 0. And we'll sum our moments. I'm going to choose F this time. Same reason as last time. I'll have negative T dc times 3 plus bx times 1.5 equals 0. So then those three equations go with that one. And now you could start substituting like crazy. Or you could use your solver, which is what I'm going to do. So I'll have 1800. And I'm going to go through, actually, before I use my solver, I'm going to say TDC is X, TEF is Y. Okay. Then I need to figure out some values for AX. Oh, let's make it Z, just to be confusing. And let's make AY T. Yeah, if you have an inspiring. Good for you. And let's make BX little b. And let's make BY J. I don't know. Okay? So here we go. I think it's good to do this on these because you want to keep track of all those different letters as they go in your calculator. Ready? 1800 minus X minus 0.8Y plus Z equals 0. Catalog and 0.6, uh-oh, forgot to put my Y on here. Y plus T equals 0. Catalog and 1.5x plus 3z equals 0. Catalog and moving up here, x plus 0.8y plus alpha b equals 0. And alpha j minus 0.6 y equals 0. And negative x times 3 plus alpha b times 1.5 equals 0, comma, curly brackets, x, comma, y, comma, z, comma, t, comma, alpha b, comma, alpha j. Close the curly brackets, close the parentheses, and hit enter. And I have a syntax error. Let's go find out where I messed up. Ah, right there. I had a doubled negative. Okay. So what did I find? I found that T is equal to negative 2700. X is equal to negative 1200. Y is equal to 4500. Z is equal to 600. B is negative 2400. And J is 2700. So what does that tell us? Okay, so T was, this is AY. X was TDC. Y was TEF. Z was AX. B was BX. And I'm assuming J was BY. Okay. Did anyone get those values besides me?
I did.
Sophie did? All right.
Brandon.
Brandon also got those values.
I appreciate it.
Someone need validation much today?
Man, it feels good.
Okay. That is all in newtons. All right.
So let's just find that, like, you have a ratio of, like 3 to 4, like it matches, so 1.5 to 2, right? That was the ratio
Yep.
of that triangle.
Yep.
And you know, but you just need those components, and then you can put those in here. I'm just trying to figure out how to use that. You're using it 0.8, 0.6, which is just 3 over 4.
Yeah, so as soon as you figure out that you have a triangle that's any multiple of a 3, 4, 5, right? So like a 6, 8, 10, right? Or 12, 16, 20. Any of those triangles are just a 3, 4, 5. And so then, yeah, you can simplify it down to being, yeah, 0.6, 0.8.
You don't need to do, like, square roots and stuff.
Yep.
Would we have to include the 1800 newtons in the moment equation? Since it's like not right time.
Wouldn't we have to include the 1800 newtons in the moment equation? Hot dang, we would. Right here. These are completely wrong, everyone. I fundamentally flubbed, right? Because I said I summed the moments about E, and I neglected to take into account the fact that we have this distributed load. Thank you, Lance. What a hot mess. Okay? So 1800 newtons, that's going to act in the middle of this 4.5 tall board. So that's going to be 2.25 down from the top, right? So this is going to be 2.25. We know that this is 1.5, so that means that the distance between here and where we were summing the moments is going to be 0.75 meters. So I need to change this equation down here to not be equal to 0 yet, but to have plus 1800 times 0.75 meters equals 0. So I can go back. Whew, so glad I didn't solve this using matrices, right? I'm going to put this back in here, and then I'm going to scroll all the way back to the third equation. I think this is going to be, yep, it's this one right here. So it's going to be plus 1800 times 0.75. Okay. Has to think about it. And here I find that AY is negative 2025. TDC is negative 900. TEF is 3375. Ooh, look at that. AX is 0. BX is negative 1800. And BY is 2025. Whew, Lance, thank you. I would have had to give you all A's on the final if you hadn't told me that. Just kidding. Oh, thank you. Yeah. Rookie mistake. Wow. Choking on my own shame. All right. So I think we'll stop our review there. I think, it's unlikely, if you're studying, it's unlikely that you're going to have a problem this simple, right? Where I'm asking you to find 3D forces or equilibriums or anything like that. Far more likely that you'll have a problem, like this. Same skill required, right? But you need to then also say some of the forces in X, Y, and Z. So, people always ask, well, will stuff from the first 2 chapters be on there? No, I'm not going to ask you a problem like that, but you sure got to know it in order to do this. Okay? So this problem seems like a reasonable problem to me. Good example of a problem. So does this one, right? The moment about a specified axis. That's a good one. I thought that this was a pretty solid, reasonably difficult shear and moment diagram. I'll guarantee you're going to have to do a shear and moment diagram on the exam. Potentially with a triangle. Yep. This was the frame and machine example we just did. That was a good frame machine problem. You triple dog dare me to not put one with a triangle on it. Interesting. Okay. 3D equilibrium, something along those lines, pretty reasonable. Okay. You'll have an hour 45 for the exam. And I will keep it to maybe an hour 50. I'll give you 10 minutes because I have another one right at noon. So ours is 10 to 11:50, and then I'll have another one at noon to 1:50. Okay. Calculators are allowed. No notes. Don't think you need any. You should know this stuff. So as far as things to do over break, since I won't have much time to yap at you, most of you are going to be transferring, at the end of this year. So now's the time to be filling out applications. Winter break is a great time to get your application into wherever you want to transfer to, fill out your financial aid stuff. I know PSU's financial aid deadline is February 1st. Okay, so typically next term is a pretty heavy quarter because you have 2 engineering classes typically. That would be strength of materials and electrical fundamentals, unless you've already taken it. Okay, so it's can be a heavy term for folks. So I encourage you to use your time on break to relax, have some fun, but also fill out get everything done for your, or as much as you can get done for transfer stuff. Okay. Yeah. That's all I have, I guess. I'll see you Monday. All right.